So for our next speaker, we have Mateusz Nowakowski. He is a senior software developer at Mangata Finance. He's gonna show us how to customize the order of the transactions in Substrate blocks. So welcome, Matteusz. I'll let you take it from here.
Hello, everyone. Glad to be here. So the topic of the speech will be modification of block execution. My name is Mateusz Nowakowski. As already mentioned, I work in Mangata. We are building a decentralized crypto exchange that is protected from bunch of different attacks that currently other exchanges are suffering from. Mainly front running, and basically what we are doing is mainly about preventing the advantage that block builders have regarding reordering transaction, rejecting some transaction and replacing them with their own, and basically things like that. You can read a little bit more about it on our webpage or on our blog, but this is a serious problem these days, and on the other side there are users that are suffering because of the increased transaction fees and the worse exchange ratio. So we modified block execution within Substrate framework a lot. So in Mangata, we separated block construction from block execution. So now these are two separate steps. Block execution is delayed by one. We introduced extrinsic shuffling. So block builder, when he puts transaction, collator, when he puts transactions into the block, he can't really know what will be final execution order of the transaction because of the shuffling mechanism. And also we introduced the concept of encrypted transaction. So as you probably know, currently you can query the node and ask for all the pending transaction. You can look into it and do something about it. With encrypted transaction, this will be no longer possible. So let's start with a short introduction reminder. So as you probably know, we have this runtime and native part of the Substrate node. Runtime part is mostly about the state transition logic. It's compiled to WASM, and basically it's the logic that defines how the blocks are executed. On the native side of the node, we have peer-to-peer communication, RPC, consensus mechanisms, and things like that. We'll get back to this to those two in a moment. But what does it actually mean to execute the block? So there are three steps: initialization, execution, and finalization. And these are mainly related to how pellets are implemented, because in most cases they require some initialization to initialize internal state to have some variants fulfilled. Then the execution happens, so all the extrinsics are executed one by one, and eventually is the finalization step, which is about cleaning up after work that has been done, also some post validation checks, and that's how it is basically. Another reminder: so block consists of header and list of extrinsics. Extrinsics are just transactions that can be submitted by the users, or some inherents that are included by the node itself. And header consists of number of fields like block number, checksum of all extrinsics that are stored inside the block, hash of the expected state of the storage of the blockchain after block was executed. The parent hash is just previous hash, and digests are some hand information that are not very relevant in our case. So we'll get into assignment and what we'll do out presentation in a moment, but just to kind of put some light on it. So if it comes to block execution, there are a number of crates that are really important, and we can divide them into two parts. One is the already mentioned runtime part, and there are frame execution crate and frame system. Frame system can be considered as a bit lower level crate that is actually executing all the transaction. In fact, it keeps track on everything related to block execution. So which transactions are being executed in which order, and eventually it can produce block header that is compatible with all the transactions that were executed. Frame executed is a bit more higher level, and it interacts with the frame system. On the native side, there is very important distinguish, because there are two separate pipelines depending on if you are producing the block or if you are importing it from the network. And yeah, here we can see the execution flow for the block producer pipeline. So basically, basic authorship crate instantiates block builder. Block builder interacts with the runtime part. Then the basic authorship palette is feeding block builder with inherents that will be converted to the extrinsics and included into the block. And then within time limit of given slot, basic authorship palette is fetching transaction from transaction pool, passing them to block builder, and when the time slot is finished, the block is being built, eventually finalized and published to the network. On the other side, there are following nodes that are just receiving the block from the network because it wasn't their turn to create one, or they are just following the state of the blockchain. And here it's mostly about validation. So when the block is received, we are doing some pre-validation step, making sure that it's the correct block. Then we are executing the extrinsic, and again performing some post-validation to verify that the state we have after executing all the extrinsics matches to what we expect, to what's stored inside the header. All right, so that was short introduction. So I really would love to explain all the changes we did in Mangata, because I think it's a very interesting topic, but we don't have that much time. So let's focus on some simpler assignment that I can present here, and that will be that you can consider like a good introduction to what problems you would have to solve if you dive into that topic, and what are not obvious problems you need to handle. So in origin implementation, all the extrinsics, all the transactions that are stored inside the block are just executed in the order they are stored. That's how it works by default. So what we would like to achieve in our small assignment, we would like to reverse the execution. So we still want to maintain the origin order of the extrinsic within the block. We only want to execute them in a reverse order. So let's take a look what implications it's related to, it introduces, and how to handle them. So first of all, we need to modify block builder, because that's the crate that is responsible for actually baking new block. And by default, it's fed by basic authorship crate. It tries to apply the extrinsic, and if it succeeds, the state is committed, and it's waiting for more extrinsic within the time limits of given slot. So instead of immediately committing the state after extrinsic was executed, we'll be rolling it back. And when one decides to finalize the block, when the build method will be called, we'll just take the list of all the extrinsic, and we'll execute them in a reverse order. So that seems like a easy thing to do. So we are running the node and everything seems to be working, but of course there are problems. So the above console is from the block builder node, and the below one with the errors is related to following nodes. And of course, there is a problem with that is related to pre-validation of the block, because we modified how block is being executed, but these changes are not reflected in other crates. And in that particular case, it's related to frame system. By default, it keeps track of all the extrinsics that are being executed. And when one decides to finalize the block, it uses that information to actually calculate the checksum of all the extrinsics that are stored inside the block. But on our side, in the block builder, we modified the execution order, but we are still maintaining the origin order of the transaction within the block. So that needs to be aligned. As you can see here, those code samples came from frame system, and there's the ref extrinsic method that basically takes list of all executed transactions between block initialization and block finalization, and it's used for calculating extrinsic checksum, basically. So we just need to do a similar thing to what we've done in block builder. We just need to reverse their order in order to get the proper checksum. So that was straightforward. So does it mean we solve all the issues? And of course not. There is another problem. This time it says storage root must match that calculated. And that's also related to block execution, because as you already know, there are two separate pipelines. One is for scenario when you are building the block, and the other one is for the scenario where you are importing the block. You just received it from the network. So we already made changes to block builder pipeline. Now we need to adjust block import pipeline in a proper way to have matching storage state after a whole block was executed. Because in that particular scenario, what's wrong is the storage state. That is, so all the transactions are just high level abstraction over key value storage. That is that represents the state of the blockchain. And after executing the block, the expected state root doesn't match one we expect it to be. So to fix that problem, we need to dig into frame executive, and it's also not very complicated. So when we want to execute the block, so when we are passing the block to the runtime part of the node, and we are fetching list of the extrinsics that are inside that block, we just need to reverse them and execute them in the reverse order, the same way we are doing it as in the block builder crate. So let's go through what all the modifications we did. So first, instead of immediately executing extrinsics in a block builder crate, we were just recording them, and once we reach the time limit for given slot, we executed list of those already recorded extrinsics in a reverse order. Then we needed to fix block prevalidation mechanism, and we did that in the frame system because of the origin implementation that assumed that the extrinsics within the block are stored in the same way they are executed, and we changed that, of course, so alignment was needed. Then we fixed the block post-validation, which was basically the same change we did to the block builder in block creation by a logical pipeline. We needed to reflect those changes in the block import pipeline on the runtime part in frame executive palette. And I verified, and that solution seems to work. So it feels that we are good. But Besides all the crashes we may expect when running node, running multi-node setup, submitting different transactions, there is another level of problems, which is more like there are more things you need to take into account when you're dealing with modification of block execution. That's also one of the problems we had. So let's assume simpler scenario. There are three actors, Bob, Alice, and Charlie. They're submitting their transaction to the block. We reverse the order of the transaction. But let's assume that I'm Alice. I just bought some Polkadot tokens, and I want to send them to the Bob. So I need to do that in two separate steps. So first I'm buying the new token, then I'm sending it to the Bob. And from my perspective as a user, it should work because I did it in some particular order. So there should be no problem with that. But if we blindly reverse the execution order of the extrinsic, the transaction will be executed in the other way. So we'll try to send the tokens to the Bob before we even bought them. And that will fail, of course. It won't cause any problems on the node side, but the result will be that one of the extrinsics will fail. So how can we solve that? We can solve that by reversing all of the extrinsics, but maintaining the origin order of the extrinsic from particular users. That would be ultimate solution, and assuming that we implement that, everything should be fine. But how can we do that? How can we actually look into extrinsic and find some interesting information? All the crates within the Substrate framework are implemented based on type boundaries limitation. And if we look into extrinsic trait, there is no really helpful information for us. There is only method is signed that informs us if a transaction is signed or not, and nothing else. But we actually want to know who is the signer of given transaction. So how can we do that? And the answer is there is only one place within the Substrate framework where you have access to fully qualified types that implements the extrinsics that are used as a type boundaries in different crates. So the runtime of the node is the only place where you have actually access to fully qualified types, to all the information, and all the informations are there. And if we look for some specific implementation of extrinsic trait, most likely it's unchecked extrinsic. And inside that one, we have access to signature and to function call. So we are good. We just need to somehow, from the native side of the node, we need to somehow fetch that information. And in Substrate, we can use a Runtime API for that. So how it works? We are defining new Runtime API. We are basically defining a single method get signer that takes extrinsic as a parameter, and it returns optional account ID. So it's basically who signed the extrinsic. And as all the runtime APIs are implemented within the runtime create runtime module, we can have access to fully qualified types. So as you can see on the code sample on the right, we can read information about signature and point to the specific field that is related to who actually signed who is actually the signer of the extrinsic. From that point, we just need to make use of it. So we need to we just need to extend type boundaries for block builder. So beside block builder API, we want it to be able to use our API. We know that in Substrate there is only a single runtime instance, and it implements all the runtime APIs. But for particular crates, we only want to make use of some limited set of those. And in that case, so far it was only block builder API, and now we need to extend it with our API that we just created. And once we have access to, once we get access to our signer API, we can interact with that API through the API objects that can be instantiated through the runtime, through the client, runtime client. And using that information, we can just take list of the all extrinsics, reverse them, and then find list of the all accounts that submitted extrinsic within a given block and reverse their order. So we'll end up with all transactions being reversed, but the origin order of the transaction for particular account will be exactly the same as when a user was actually submitting the extrinsics. And that's it. That's ultimate solution for our problem. And basically, we've done what we expected. So thank you one more time for attending this talk. Here is again our website. Mangata Finance. You can also reach me out through an email. And yeah, if you have any questions, please share.
Awesome. Thank you so much, Matteusz. It was really, really great talk. We don't have a lot of questions right now from the public, but yeah, I want to know a little bit more. Like you just mentioned here, you are giving an example of the part about like reversing the transaction order. Like, how are you really using something quite similar to prevent like front running? Because front running also requires to modify all these block execution, but yeah, it's kind of also a really hard challenge.
Yeah, so on our side, we are actually shuffling the extrinsics. So when you're a block builder, you can include the transaction into the block. You can reorder them the way you want. But in our case, we separated block execution and block building process. So whoever is building the block, he don't know what will be final order of execution because it is decided only in the following block and only using information that is available at this point in the following block. So that's one of the changes we did. So yeah, basically. So block builder can put any transactions and any order he wants into the block, but those will be executed in the following block and they will be shuffled. So for example, that can partially solve front running problem, for example, because in front running, you need to make sure that your transaction will be before and after some particular transaction to get some gain out of it. So when you're shuffling, you no longer, when we are shuffling, attacker can no longer know where in which order all the transactions will be executed.
Okay, yeah, that sounds really, really interesting. Yeah, it may bring a few other issues, but yeah, I cannot think right now about anyone. So yeah, there are here two questions from the audience. So one is, if the client will execute transaction in different order, but resulting in the same storage changes, will it be considered a valid execution or will cause an error?
I mean, it's something that you need to decide, because if you're getting the same state, maybe it's fine. But on the other hand, if you're reversing or as we do, if you're shuffling, you probably will implement some extra pre and post validation, and such block would be rejected. But if it's only you who is modifying the code on your side, and you want to execute the transaction in some particular order different than suggested by the network, I think if you end up with the same state root, your node won't crash. But I can't really think of how to do that. How to know in which order I can execute. How can I execute transaction in different order than suggested by the network and end up with the same state? That might be challenging. Even because underneath it's just a Merkle tree that represents state of the network. So it's really easy to be a different state that just changing the execution order and changing the way the key value pairs are persisted in the storage results with different hashes of the state root. So it would be really challenging to find such cases where you can do that, when you can do that.
Okay, yeah. So you mentioned that in your case, you do some shuffling. How do you are able to end up doing this? Because if I just said, if not all the nodes agree at the end with the same transaction order, there could be some issues on the consensus. So how do you agree that?
Yeah, so what we do, we actually delay the execution on given block by one. So block is announced, but it's executed with one block delay. And this one block delay, we are using it to publish some information that when the following block will be received, everyone can fetch information from the following block to properly shuffle the extrinsic from the previous one. So the reasoning about consensus, and it's solved basically. The only problem is how to generate this shuffling seed in a way, because we can think of it that even by separating block building and block execution process, someone decides about the shuffling seed that is used in the whole network. And he can choose such value that will end up in an order that will give him some profits. And we are also preventing that by doing some cryptography. So in our solution, we are publishing some shuffling seed at some point, and whole network can access it and is using it for actually shuffling the extrinsics, but we doesn't allow to randomly pick this value. It's already set and stored. I mean, it's set in the storage, and everyone can verify if someone was trying to provide some wrong value that will not pass validation. So we are shuffling blocks with shuffling seed that is being produced in the following blocks, and in the same time we are not allowing to manipulate that value.
Awesome. Thank you so much. We don't have any more time for more questions. It was a great talk. Thank you so much.